come to polarization of the ions, we also have to talk about charge density. And in charge density, we'll have to talk about some rule called Farjan's rule. And Farjan's rule tried to explain to us the factors that will affect the polarization effect of different ions. I want us to talk about two ions here, two groups of ions. One, the cations. These cations must be the polarizing agents. Polarizing agents, they are supposed to cause polarization. I will shortly explain what polarization is. And then anions, on the other hand, are the ions that are polarized. These are the polarized ions. So it means that what polarizes cations polarizes anions. Now, according to Farjan's rule, he puts two conditions or two factors that affect polarization effect of different ions. And because we have to talk about the polarizing agent, that is the cations, and the polarized ions, we are going to group these ions into two groups. One, we are going to talk about the cations. Now, on the cations, what affects the polarizing power of a cation? A cation, one of these things is a smaller radius, smaller ionic radius, smaller ionic radius. So an ion with a smaller ionic radius will have a greater polarizing power. Number two is a bigger charge. So a bigger charge on the ion, on the bigger charge on the ion. So for cations, an ion with a bigger charge will have a stronger polarizing power, and an ion with a small ionic radius will have a bigger or a stronger polarizing power. Now, you realize these two factors, we still come back to charge density, because charge density, we said that the charge density is directly proportional to the charge, meaning the bigger the charge, the more charge density it has, and also the smaller the radius, because charge density is indirectly proportional to the radius of the ion. So it means that the smaller the radius, the bigger the charge density, and that's exactly what we are talking about in Farjan's rule here. So again, here we have to understand that if ionic radius, if an ion has a small ionic radius, for example, if I put down these ions, one is sodium, the other one is magnesium, and then finally I have aluminum ion. These are cations. Sodium here should be having around 0.102 the ionic radius. This one should be 0.072. This one is 0.054. So we realize that comparing the sizes of these ions, aluminum ion has the smallest ionic radius, and therefore, according to what we have said here, in this group here, or this period, sodium, magnesium, and aluminum will be able to have the smallest radius, and I said the smaller the radius, the bigger the charge density. So we can say that therefore aluminum, in terms of radius, aluminum ion will be the one that will have a stronger polarizing power. Then when it comes to charges, we have to know that there's a factor here, the charge on the ion. This one has a charge of 1, this one a charge of 2, this one a charge of 3. Again, in the list, we see that aluminum is the one with the bigger charge on the ion. And I said here, the bigger the charge, the greater the charge density. And therefore here, whichever factor we look at, whether we look at charge on the ion or radius of the ion, aluminum still comes out as the strongest polarizing power. Now let's look at what is polarization. We have explained polarizing power, we have explained which one it has more polarizing power, but what is that polarizing power? What is polarization itself? Now, to explain what polarization is, I want to mention something called electron density. Electron density. Electron density is the probability that an electron will be found in its specific position. Now, if I have a sodium ion here, sodium ion has lost one electron, so it has 282 or 28, sorry, that is before this ion is put closer to an ion, because we know that when this ion is separate completely alone, the electrons will be grouped in terms of orbitals, and we say no, each orbital has 2 electrons here, so we can say that is 2 electrons, another electron, electron there. So these electrons are grouped in a very regular manner, and these lines, what we call the energy shells, these lines I'm drawing here to indicate the energy shells, we can call them what we call electron contours. Electron contours. They are just lines we draw to indicate the position, the possible positions of the electrons. Now these electron contours, we can see that now electron contours in this way here, they are kind of circular in manner, in a way that we can tell that these electrons are where we expect them to be. But if you bring this electron to an ion, for example, a chloride ion, which also, before these electrons are put together, the electron contours must be generally evenly distributed. So if this is chloride ion, having 2 electrons here, there, 2, 8, 7, let me put one here. This is the electron distribution on a chloride ion, and you can see, let me have an X to show that that X has come from the electron lost from sodium. So in this case here, we say that this is the polarizing agent, it's the one that causes polarization on an ion, and this one is the polarized ion. So in this case here, before this ion and these ions are put very close to each other, we expect the ion distribution here to be very even the way it is. So electron density in this particular case here is much more distributed in an even manner. So we can get a fairly regular shaped electron contours. But when we now carry this electron and we carry this ion, we bring it closer to the cation here, then we start seeing something happening. So we can have, if you have chloride ion here, the chloride ion here is here, 2 electrons, 8 electrons. If you bring this ion, the chloride ion now closer, they are forming ionic bond here, something strange happens. The stronger, we know that compared to this chloride ion here, the size is much bigger than this. And therefore, if the size is much bigger than this, it means that the attraction to the nucleus from the outer energy shell is much weaker compared to this. We talked about the charge density is a factor of ionic radius. So it means the smaller the ionic radius, the stronger the pull towards this nucleus. So this is much more stronger than this. Now if this is much more stronger, it means that this ion here can be able to pull the electrons from the other cation towards this area here. So we'll start seeing, from time to time, we'll start seeing, if I may remove this bracket here, we'll start seeing some kind of distortion in the shape. Distortion on the shape because this positive charge is trying to pull these electrons. So you don't expect these electrons to be where they were before because they are pulled towards these other corners. They are pulled towards this other direction, and if the polarizing power of the cation here is much more stronger, with the time we expect that this anion will be pulled until there is kind of overlapping. It could go until we expect an overlapping kind of arrangement here, where some electrons are now pulled here, forming what we may call a partially covalent bond. Partially covalent bond. Now I said that this concept will be much more explained in book 2, that is in A2 level. For now, we'll just have to say that once the electron contours are distorted, they are distorted because electrons are being pulled towards the cation. The cation seems to be much stronger, than the anion. If the anion is also strong and the cation is much stronger also, we don't expect this distortion. We expect a purely ionic bond where we have like brackets, and the electron density on the other side and the electron density of this other side will clearly be very, very uniform. But if the anion is weaker and the cation is much stronger, we expect that this the electron density will be distorted. I talked about the electron density. We'll be explaining the possibility or the probability of us getting an electron in its specific position. But in this case here, if you look at this electron, when I drew it down here earlier, the electrons were much more evenly distributed. But in this case here, you'll find most electrons coming here. They are coming here to kind of form a bond, and a covalent bond, because they are being pulled by the cation here. So that is what we call polarization. So if someone asks you what is polarization, polarization is the distortion of the electron contours or the electron density, especially when an ion is closer to a cation with a very strong polarizing power. So what is polarizing power? Is the possibility of the extent to which a cation can be able to distort the electron density of an ion. That is what we mean by polarization. Earlier, I'd explained factors that will make a cation a much stronger polarizing agent, and I said it depends on smaller ionic radius. The smaller a cation with a small ionic radius will be one with a stronger polarizing power. Then I said one with a bigger charge. And according to the ions I listed before, that is sodium, aluminum, and magnesium. We said magnesium having the smallest ionic radius and also having the biggest charge will be the strongest polarizing power if you compare the three ions I drew before. Now let me explain those factors that will affect polarization of anions. Now, according to Farjan, it's actually the opposite of what happens in the cations. For an ion to be polarized or to be affected this way, it means that it must be able to have a very weak density, a very weak charge density. So if it has a smaller charge density, we say charge density is a factor of first charge divided by square of radius. And we said earlier, for it to be a stronger charge density, this must be smaller, while this must be bigger. So let's look at if it is weak. This is if it is stronger. What about if it's a weak charge density? If it's a weak charge density, we expect that the charge here, the charge should be smaller and the radius should be bigger. So for anions, an ion will be highly polarized if it has a bigger ionic radius. A bigger ionic radius and smaller charge. And the smaller charge. If these factors are in play for an ion, that ion will be greatly polarized or easily polarized, because therefore it has a weak charge density, meaning that the force of attraction pulling this one to the nucleus here is much more weak. And we know that this force here becomes weaker as the number of energy shells increases. That means if the number of energy shells are more, then the ionic radius is bigger, and therefore due to shielding effects and repulsion effects here, we expect that charge to be weaker. Now, we know that therefore when we have ionic bonds like we do here, some ionic bonds, we can have two groups of ionic bonds. One which are purely ionic bonds, compounds which are purely ionic, and compounds which are partly ionic, or let me say partly covalent. They are ionic and they are covalent as well. That means that some part of that ion behaves like an ionic compound and partly it behaves like a covalent bond, and we know that only can arise due to what we call polarization effect of different ions. Viewers, I think that's an explanation enough, and we meet next time to look at more cases about